Hello everyone. We are Team AAA and we have chosen the project 5, which is data prefetching for spec, SAT solvers, graphs, and servers. The project aims to improve the IPCP prefetcher that won the third DPC championship. And we try to improve it for various workloads such as spec, graph-based workloads, SAT solvers, and servers. Uh, yeah. Uh, these are our expectations on various workloads. We think that spec will have normal programs that are various kind of applications, normal applications. So the memory pattern might be more regular compared to graph and SAT workloads. Graph and SAT workloads, they are usually more random. The memory address, the consecutive memory address might jump a lot. So, and servers also, we think that it will be more towards the random accesses, because many clients will be connected at the same time to a server, and each client's associated data might be at a different memory location. So the server, when it's processing multiple things, it might have to jump around a lot. So we think that it might have more random accesses. And we tried to improve the IPCP paper on three fronts. Like one is improving the complex stride class of the prefetcher. The other place where we try to improve is the page related stuff. Like, we'll explain more on this when we later. And the third domain is miscellaneous changes like reordering stuff and changing some values. So, Atharva.
Yeah, so the first observation we made while going through the paper was low IPC corresponded to a higher fraction of the strides being classified as complex strides. So our hypothesis was to reduce the number of misclassified complex strides. So our solution was, so the signature Zor stride was the quote-unquote feature that was being used by the complex class, or that was being used by the prefetcher to classify the stride as a complex stride. So we thought the only signature-based hashing might not be enough for the prefetcher to learn all the aspects of the access pattern. So we, in our implementation, we added two more features, that is a PCs or previous PCs or previous PC. So and the second feature we added was page address or confidence. So the way we do this is update the confidence of a particular feature. The actual stride measured by the prefetcher is the stride that is predicted by the prefetcher, and take a weighted sum of all the confidence. And if it is greater than a threshold, then prefetch. The heuristics behind choosing these two features was, for the first one, that is PCs or previous PCs or previous PC, is that this will help the prefetcher have an idea of which PC values generate memory access, and taking a Zor with the previous memory accesses PC value would help it have some idea of the history of PC values. And page, we decided to implement some page-based feature because graph algorithms have complex memory address patterns ranging across pages. So if the prefetcher is able to somehow learn the page information and the complex page access patterns, then it might be helpful. Another miscellaneous change that we made here was reordering of the classification or reordering of the checks whether a particular stride belongs to a particular class. So first, the complex stride was being checked at a third level after constant stride and after global stride and constant stride. So we made the complex stride first, then the constant stride, and then the global stride. So these were the overall improvements in the IPC that we got. This is for graph workloads. That is after implementing the two features. And we see a significant decrease in the L1 miss rates across all the traces. This is the improvement in IPC that we achieved only after implementing the first feature, that is PC-based feature, which we assumed would perform better on spec traces. And as expected, there is a decrease in L1 miss rates across all traces.
So this graph shows the distribution of classification of each IP. Or you could say we take the total number of prefetches that have been done. We see the source of prefetch, which class of prefetch it belongs to. So this is the distribution that we got for graph-based traces on the original IPCP paper. Now, after adding the PC correlation, that is Zoring with PC, its previous PC and previous PC, we saw that the complex stride pattern reduces a lot, like diminishes to almost zero. Why? Because since we are increasing the strictness of the condition for it to go to the complex stride, it has altogether reduced finally. So that's the reason it has become almost zero. And yeah, it is almost zero here. This was L2 cache. Here it is clearly seen that it is almost negligible over here. Right? This is for the L2 cache. Yeah. So basically, after reordering the various prefetches, the class of prefetches, like making complex greater than constant stride greater than global stride, we have observed that the IPC has jumped, like it has improved a lot on the graph-based applications. And we have also observed that the number of strides classified as complex increased, and the number of strides classified as global almost diminished to 0. Why? Because we think that the first one, whichever class of prefetcher is given the highest priority, that one kind of has an edge and kind of dominates. Like suppose a prefetch goes to the global stride. If the confidence of global stride is low, it goes to the constant stride. If it's still low, it goes to the complex stride. By the time it goes to the complex stride, the overall confidence itself reduces. So there's a high probability that like the overall probability itself reduces. So it might, for most cases, it doesn't even reach the confidence level of confidence threshold of complex. So that's the reason it passes on to the next line. That's why we observe that the third one, whichever it is, it has really small effect. So reordering really changes the distribution of prefetches over the classes. Yeah. Now we move on to the second type of prefetch improvement that we explored. We thought we dealt with pages. A page is basically the way OS deals with the memory. Whenever OS has to load some memory into the DRAM, it takes the entire page from the off-chip memory, which is hard disk or SSD, and puts the entire page in the DRAM. So it can happen, and it does happen, that the continuous bits of memory, the so-called continuous bits of memory that we code into, they might be at various places in the DRAM, like they might not be adjacent to each other. So this causes some discontinuities in the memories. So especially in SAT and graph places, this causes a lot of jump arounds all over the memory and all over the various pages. So our idea was, if a same page is accessed for n consecutive times, n is something like 3 or 4 or 5, it's arbitrary, we have prefetched the entire page. The entire page is not prefetched at once. If we issue all the prefetches at once, it will just overload the prefetch queue. So we have done it like over some time. But as we can clearly guess, this ends up kind of dumping a lot of stuff from the memory. So it ends up polluting the cache. Since a usual page is of 64 kilobytes, we can't prefetch it into L2 cache or L1 cache. It will end up occupying most of those caches. So we prefetched into LLC cache. But still, we didn't observe great improvement in performance, because there's a lot of cache pollution going on. To reduce that, we'll have to go to more refined strategies. This is a very crude one that we could think of. Like we should refine this to make it better. And we have explored these refinements over the internet, but we couldn't really implement them. So I'm just this slide is just about that. And
so if you recall, we experimented through increasing the strictness, or making it increasing the strictness to enter to be classified as in the complex class. So we thought, why not remove the complex class altogether? It seems like a very weird idea, because the complex class is one of the unique things that was proposed in this paper. I think it's unique because I haven't seen it anywhere else. But yeah, so we found out that it worked very well for some places where the number of the classification was made. The classification was made kind of with a low confidence, because in the code the confidence was just greater than 0 and it was classified. Yeah, in those cases, in cases where it was actually incorrectly classified, removing the complex classification altogether did pretty well. But you can guess for most other cases that it's slightly reduced or even somewhat drastically reduced the IPC values. And we also went in the completely opposite direction, even though it was given in the paper that implementing complex in L2C wasn't a good idea. But yeah, so one reason we could think of was because there was a low threshold already to classify it as complex. It was sending it to L2 with that low threshold, and there were even more requests being made based on those classifications, which isn't a good idea. Which isn't a good idea for traces with a large number of inaccurate complex classifications. And also in one of Biswasar's papers, he explains it in terms of the degree of prefetching, and saying that complex requires a lower degree, so it must be prefetched later on, and unlike the constant stream and the GS classification. So that is the reason why we don't put it in L2.
Yeah. So another observation that we made is that next line prefetcher is being used a lot. Like many times, the next line prefetcher is significant. So that's the reason we thought of improving the next line prefetcher using some ideas of best offset prefetcher. So basically, we try to observe the past 100 calls to the prefetcher, and we take delta. Delta is nothing but the current address minus the previous address that has been called. We observe these deltas, and the most frequent delta will become our current offset. Like we'll prefetch current address plus that offset. So this is justifiable because there's a high chance that the most frequent delta will again hit successfully. So this is a slight improvement over the next line prefetcher, and it gave a good improvement when for some of the traces. So here is one such experiment that we performed. When the prefetch classes were reordered, we observed that global stream and constant stride were a bit diminished, and the next line prefetcher dominated a lot. And actually, this gave a huge improvement in the final IPC and miss rates as well. Like this was completely unexpected for us, but improved, but the next line performed well actually. Yeah, here we show the final results, like the various changes that we made to the files, and each one we calculated IPC and various other parameters. We show the we are showing the IPC values that we have found for graph-based traces over here. The green shows an improvement. This is a relative IPC, by the way. Each entry in this is IPC of that particular file divided by the IPC of the original file. So this is an greater than 1 is an improvement and less than 1 is a decrease in performance. Yeah. So finally, we found that two particular files were giving a really good performance jump. Those particular files correspond to the reordering of priority and reordering of priority along with modifying the next line to make it more similar to the best offset prefetcher. These two are giving really great improvement. This is a 12% improvement over the original paper, and this is a 2% improvement. We see that most of our strategies were kind of decreasing, but yeah. Finally, I conclude by saying that we enjoyed the project. Like we couldn't explore all the things that we ideally wanted to, but we actually wanted to try to implement temporal prefetching also, but it wasn't feasible. Like we found some resources also, but we couldn't implement because of time crunch. But yeah, the project was definitely fun and full of surprises because almost all the things that we predicted were wrong, and everything that improved caught us by some surprise. After that only we tried to justify those things. So yeah, thanks a lot.